For this video, we need some familiarity with vectors and their projections. If you're not familiar, I'll give you a quick summary. Suppose you have a point x, y. Think of a vector as an arrow going from the origin to that point. A vector expresses distance and direction. In what direction and how much do I have to travel to get to that point? In this case, you travel x units along the x-axis and y units along the y-axis to get to the point x, y. And note that we write vectors with brackets. Now let's say we have two vectors x1, y1 and x2, y2. An important question is, how much distance and direction do these two vectors share? They both go some amount along the x-axis, and then some amount along the y-axis. After that, they diverge and go in completely different directions. The part that's shared among both vectors is what's common or similar between both vectors. There's a mathematical way to find the similar part. It's magnitude of the a vector times the cosine of the angle between a and b. But don't worry if none of this makes sense. The takeaway is there's a mathematical function called proj, or vector projection, that quantifies how similar are these two vectors. And note that even though our example was for 2 dimensions, it works for as many dimensions as you want, 3, 1000, or any number of dimensions. Now let's take a massive step forward and discuss how models learn meanings behind words. This is a foundation for AIs that can talk like humans. There's an idea from linguistics that similar words appear in similar contexts. For example, The Weeknd is a famous pop artist. The words weekend, famous, pop, and artist all appear near each other. We want to capture that they're all related. Computers are not great at operating on English words, but great at operating on numbers. A breakthrough idea was to train a model to map words to high-dimensional vectors. This technique is called word vectors or embeddings. Vectors are the perfect medium for expressing similarity. If two words are similar and frequently appear in the same context, then we want the vector projection of one word onto another to be high. And if two words do not frequently appear in the same context, then we want the projection to be low. The word vectors are our model parameters, so we tell our compute nodes, which we've previously analogized to monkeys randomly typing, to go and generate random sets of word vectors. Now, to grade how good a set of word vectors is, we need training inputs and outputs. We scrape the internet for English texts. We might see a passage starting with, "Weekend is a famous something." We'll take all pairs of words in that brief context and use them as inputs to the model. And those pairs of words are all listed above. Now say we have the pair weekend and famous. We make the model map these two words to their corresponding random generated word vectors. Then we make the model perform a projection calculation. The higher the projection output, the better the score we give the model. We essentially reward models producing word vectors that show the words weekend and famous are similar or related. This could take some time to understand, so feel free to pause and rewind if you need to. Now, on the other hand, we also generate pairs of words randomly, such as these ones above. Random words are expected to be unrelated, say weekend and pug. We send these pairs through the exact model as before, but this time, the lower the projection outputted by the model, the better the score we give that model. We're essentially rewarding models that also generate word vectors showing that the words weekend and pug are unrelated. Side note, we do need advanced math to discuss how the monkeys can search better than randomly generating word vectors. I'll cover this in later videos. And the formal presentation of the model is slightly different and more technical. I find this setup more intuitive to explain. So for now, just imagine the monkeys randomly tried a ton of vectors and came back with a decently good set. When researchers inspected these word vectors, they observed that the higher dimensions captured various ideas. For simplicity, you could think of the x-axis dimension as the fame idea, You might have celebrity and famous on one side of the x-axis and unknown and obscure on the other side. The y-axis dimension might be another idea, like arts versus science, where artist and singer are on one side and engineer and scientist are on the other. You might find The Weeknd and Lady Gaga in the arts and fame quadrant. And maybe you'll find Elon Musk in the science and fame quadrant. Finally, you might find some random names on the obscure side of the graph. Note this is a simplification. The reality is the ideas do map to some dimensions, but not the traditional XYZ ones. This is important, and I'll talk more about it in a future video. The key takeaway here is that word vectors or embeddings pave the way for computers to numerically approximate intangible ideas like gender, freedom, or pain using these high-dimension vectors. Embeddings are a key component in large language models like ChatGPT, and you will see this technique come up over and over again.